All right, so in these problems, we're going to actually create an exponential function off of two data points. So we have that the U.S.'s population on 1980 was 227.2 million, and in 1990 it was 249.5. So we're going to let t be the number of years since 1980 because that's our first data point. It's the best thing to do. So if we know our first value is 1980, then we know this would be 0 because 1980 minus 1980 is 0. And its amount was 227.2. And then we can do the same thing with 1990 by subtracting it. That gives us 10, and its value was 249.5. So if we have an exponential function and we plug in 10, we want it to give us 249.5, and we plug in 0, we get 227.2, which means we already know the initial amount. And so that's giving us our starting function. Now, if you're like, well, I didn't notice that, you can always plug it in. And so now you can see that k times 0 would be 0. This would become 1. And so we'd get p times 1. So p equals 227.2. Done. It's already there. So now if we transfer that over here, we know our amount. We can actually write it. A equals 227.5.2 e to the kt. And then we take and plug them in. So this is t, and this is a. So 249.5 equals 227.2 e to the k times 10. And so now we can just use exponential functions and logarithms to solve this. So first we need to isolate that exponential. So we plug that in our calculator. And it gives us 1.09815. That's good enough. E to the 10k. I just switched the 10 and the k. And then again, if you put a natural log around each of these, that allows us to bring the exponent down. And we end up with this. Zero point 0.09368 equals 10k. So if you remember that natural log in the you're basically going to cancel and give you 10k. And so now if we just divide by 10, we get 0.00. Why did I plug that in my calculator? I don't have to do that. 628 equals k. And so this translates to a 0.9% growth rate. And we could even make it a little nicer and say 9.3, 9.4. I got to round that up because it's 3.6. So 9.4% growth rate. So what's our growth rate? 9.4. They also want the exponential function. So now if we plug it back in, remember we're just plugging in our initial amount and then 0.0, wait, it's a 0.9, not 9.4, 0.94, 0.009. We'll put up there 4 just to make it easy, and then t. So there is our exponential function. So it's a 0.94%. That makes a lot better. 9.4 is a huge growth rate. So about a percent growth rate. It's not bad. And so we get this function. So now what we're going to do is estimate the US population today. Go online and compare it to see it. So right now it is 2020. And so if we subtract 1980 from that, you'll see that's 40 years. So assuming, I mean, our growth rate back in 1980 and 1990 could not have been the same that we have now. So this data is not that great. But let's just see anyways how close it is. So if we're going to plug in 40, 227.2 e to the 0.0094, and then 40, and we'll see what we get. So 227.2 second natural log 0.0094 times 40. And it says that we should be at 330.9 million. So we can just make it, yeah, let's put that 330.9. So 330.9 million. Now this is also supposed to be for July, in July, right? And We're not in July yet. I think this is April when I'm making this. So now let's go on the online and see what we get. It's 330.6. We're off by 300,000. That's pretty impressive. It's a pretty good. So you could actually estimate to see what our population would be in 10 years, and it might be pretty close. I mean, hopefully our population rate's decreasing, but yeah, 330.9 is what we had. And so that's in July, and so we've got 3 more months till July. So it's possible that we'd be pretty darn close to what it is. But there you go. This is how you do it. You just need an initial and a K, and to find the K, that's how you do it. Okay, so I want you to try this one now. And I'm going to get you started, and then you can do the rest of it. So once the population surrounded the release of a new book is over, sales of the hardcore edition tend to decrease exponentially. So it says decrease, which means we're talking about a decay. So we got to make sure our K comes out negative. And it will. You don't have to input it. It will do it itself mathematically. At the time, publicity was discontinued 2009. So that's our first year. So we're going to say T equals years since 2009. A certain book was experienced sales of 25,000 copies per year. So we already know 2009, that was 25,000 copies. 1 year later, that's 1 year later, had dropped to 10,000. So now, what will the sales be after 2 more years? So they want to know 2010 plus 2 years. They want to know 2012. What are the years in that time? So it's the same questions we just did up here. You're going to use the exact same steps to find the growth rate and then create an exponential function and then plug in the time for 2012, which is 2 years, to see what you get. So hit pause now and give it a try. And when you come back, it'll be all solved for you. So pause. So this is what you should have gotten, 92% decay rate. Plugging that in, I used a little more decimals here, and I plugged in the exact, and it gave me exactly 1,600 books. So in 2012, we should expect 1,600 books, which is obviously decreasing. It says that in the problem. And so our decay should be this as well. It's a quick little rough sketch. So 1 is 10,000, 25,000 initial. Remember, when you graph these, they don't start until 0, so don't go this way. There's no backward arrow. It starts at 0 and then decays. All right. There's how you find them. Thank you.